Welcome back to the office. We want to take a look at an example of our fundamental theorem of finitely generated abelian groups. For this example, we are going to prove, well, we're not actually going to run through the whole proof of the theorem. We want to share the ideas of the proof of the theorem. So we're saying that if M divides the order of a finite abelian group, G, then G has a subgroup of that order. And essentially what we want to do is we want to find an element that has that desired order. So let's see here. This is a little bit tricky. It's not super tricky. There's just details, so you got to kind of keep up with what's going on with each of the small pieces as we try to put it together. All right, so if G is equal to Z, I'm sorry, not equal to, but isomorphic to Z sub P1 to the R1, direct product with Z sub P2 to the R2, direct product with all the way up to Z sub Pn R to the N. Then if M divides the order of G, of course, the order of G is P1 to the R1 times P2 to the R2, all the way up to P sub N to the R sub N. And then in order to divide this, M has to be equal to P1. Oh, let's see here. We'll call it S1 times P2 S2 times P3 S3, all the way up to P sub N Sn. So it has to be some power of each of those. That power could be 0, of course. That's not an issue at all. And these do not have to be distinct either. So if we have that M is equal to this, then what I want to do is I want to identify the element, or at least show that there is an element, call it A1, comma A2, comma A3, all the way up to A sub N, right? Direct product with N groups, so N entries, where the order of A1 is P1 to the S1. Now we essentially know that this exists. A2 is, the order of A1 is this, the order of A2 is P2, S2, and so on. AN is PN, SN. Now we essentially know that this is going to exist because the order of an element in the order of this whole thing is going to be how did we say that earlier? It's the least common multiple of the orders of the individual pieces. So that will give us, right, if we have this, then that's going to give us this. I suppose we should be careful there. Because if any of these have a common factor, right, if P2 is equal to P5, for example, we should then both of those would not be necessarily included. All right. I suppose I have a little bit of a hiccup there. So maybe we'd have to iron that out. Anyway, I know that I can find an element of this order in here, because I can just take, for example, let's say I have Z sub 3 to the 4th power. That's 81. And let's say I want to find an element of order 3. Well, all I have to do is take 81, divide it by 3, and say, oh, look, 27 has order 3. You take this thing, divide it by the desired order, and it identifies exactly the element that you're looking for in there. So then you choose that to be a 1, and you do that for each of them. Once you do that, the order of this is going to be the least common multiple, which is going to be exactly this, as long as you don't have the uh, um, as long as all of your p's are distinct, that will certainly be true. So then it's just a question of when they're non-distinct. Oh, well, actually, I suppose what we can do is we can actually take, rather than the order of this particular element and finding a specific element, rather what we do, I apologize, a misunderstanding on my part, is we look at, instead of what's generated by this entire thing, rather we look at what's generated by A1, take the direct product with what's generated by A2, take the direct product with what's generated by A3, and so on. And by doing that, so we can rather than identifying this one specific element, we can identify the elements A1 through AN in their associated groups, which then give us the desired orders. And then this is going to be exactly the order that we're interested in, because this subgroup has order P1 to the S1. This subgroup or this piece has order P2 to the S2, and so on. So yeah, overall, the order of this will be exactly M, and that is a subgroup of this. And again, the isomorphism that takes us from here to G will identify that subgroup in G. Yes. All right. So that was a little bit interesting to talk through. Like I said, some of the details are kind of annoying to follow along with. So feel free to rewatch this if you need to, or follow up with some questions. But the point is we have some applications for that fundamental theorem. So I got one more example to share with you. So join me back here in the office for that.